So, quick reminder, all right, so what are we doing in induction? So, what we did, we established one key factor. We established that if there is a changing magnetic flux, as a reminder, when we say magnetic flux, we're saying here is some area and there is magnetic field lines going so for our purposes, magnetic flux is the product. Should be a sine phi there. Right. For our purposes, magnetic flux is this: take some area, force some magnetic field lines going through it, define that as magnetic flux. Principle: if that flux is changing in time, there must be an induced EMF. Those of you who don't remember EMF, that's just another way of saying voltage. And so we summarize that in Faraday's law. Let's try that again. We said the induced EMF is equal to the magnitude of the change in flux over change in time. Right. And the examples we did was, say, I've got a loop here. Here's my loop, and I'm going to.
Hey, Professor.
Yeah.
Last class you said it was cosine, and here you have sine.
Oh, sorry. That was a mistake. Make that actually legible. Thank you. Right. Right. So one example we talked about, it was of magnets moving towards a loop. Right. And I say, okay, if the magnet's moving, there must be a voltage produced on this loop. But then the question was, what is the direction of current? Right. If there is a voltage on this loop, current's going to start flowing. So does it go this way, or does it go the other way around? That's a big question we still haven't resolved. Right. And so we said, oh, let's look at this weird example of that slide bar. We said, put a magnetic field in here. I'm not going to go through this one in detail again, just a reminder that we flicked the slide bar, gave it a little V, and then tried to guess, was the current clockwise or counterclockwise? And if it's one direction, the slide bar will just get basically infinite force. It'll keep sliding forever and ever, and that's not physically possible. There's not enough energy in the universe to support that. So we said that for these physical reasons, there is a logical way to determine what the direction of current is. And now let's get to that, okay? Right. And it comes from Lenz's law. Here's how it's going to go. It's basically two conditions on Lenz's law. If the flux increases, then an induced field will be created, and the induced field will point that induced field is going to point the opposite direction. Right. So, I'm increasing magnetic flux, push back, fight that. Second case, if the total magnetic flux is decreasing, induced field points parallel, points in the same direction. Come on. Right. These are our two conditions, right? If flux is increasing, point the opposite direction. If it's decreasing, point in the same direction. Support it. So, what do I mean by the induced field? Remember, go back to this guy. This magnet moves. That creates a EMF, a voltage on this loop. If there's a voltage on this loop, then there's a current induced in this loop. If there's a current in this loop, that current makes its own magnetic field, the induced field. So now we're going to be having this game of one object's field inducing a magnetic field in the other. So it's going to be our job to keep these things straight, to keep them, make sure, are we talking about an induced field or the source field or external field is the phrase I'm going to use a lot. So I'm going to redraw that one of the magnet moving. I'm just going to rotate a little bit. So let's go for this case. Here's my loop. And I'm just going to draw just the north end of the magnet. And the north end, magnetic field in north end leaves the North Pole and comes back around towards the south. So it's going to be a picture like this. All right. And then we say drop the magnets, okay? I'm going to do that over here. So the magnet falls a little bit, it gets closer. As you get closer to the magnet, you're getting stronger and stronger magnetic fields. So now it becomes magnetic flux went up. Magnetic flux just increased. Now I have to say, well, what is the induced direction? Go back to our Lenz's law. Flux is increasing, create a field opposing that. So, come back to this picture, get our loop. The magnetic field is pointing down through the loop and getting stronger. So loop says, okay, point the opposite direction. There's the induced magnetic field. It must point up. All right? What direction of current is going to get a magnetic field in this loop pointing up? And this is going to be our right-hand rules. So I'll do my right-hand rule. Let's see here. We're doing the magnetic field of a wire. So for that, the thumb in my case will be the direction of magnetic field. All right. Index points in direction of current. Middle finger is where am I measuring the field. So I'm always going to measure the field inside the loop because I want to see the magnetic field going up like this. And I'm going to just guess the direction of current. Some of you might be clever. You might say, okay, I know if I point my thumb along the magnetic field and then go back inside, you'll get direction of current. If that works for you, good. And it doesn't work for me. So what I do is I just guess. Am I guess right? I'm happy. If I guess wrong, 50-50, right? So I'm going to guess a current. It's going that way around. I'm just going to guess. I'm going to say the current's going this way around. Does this induced current create this magnetic field? So right-hand rules now. Current. I'm going to have one going up like this. I'm going to go, boop. I want to measure inside the magnetic field, or inside the loop, and I get a magnetic field pointing up. So yes, I guessed correctly. The induced current in this particular problem is going around this direction, creating an induced magnetic field. And that field is opposing the falling magnet. Right. More examples. I'm going to finally erase Lenz's law. Let's go to a solenoid in loop. Right. So here's my solenoid.
We have a question real quick.
Yep.
What do you mean by inside the loop?
So where am I measuring magnetic field? So let's see. Let's go one step back, all right? Magnetic field for a wire is mu naught I 2 pi r, right? R, right? This is for a current carrying wire. R is not the radius of the wire. R is the distance from the wire. How far away? If I measure, you can say to the left, right? So I'm pointing to the left of the wire, and I find magnetic field coming. That's magnetic field coming out. But if I go to the right of the wire, right? Current, gotta point this direction now. Whoop, pointing down below. Magnetic field is coming in. Right? Similar thing for the loop again. Similar thing for the loop. Am I measuring inside? Or am I measuring outside the loop? That's what I mean by inside or out.
Gotcha.
How would inside outside the loop affect the direction? So A loop of current. A loop of current looks like a north-south bulb. I have current doing this. All right, look at what's the magnetic field. Well, inside it's doing that. Which means on the outside it's doing so if I measure inside this loop, I see magnetic field going up. If I go outside the loop, right, I go outside, I see magnetic field going down. I'm gonna erase the left board and start the solenoid loop example. Right. So here's the setup. I'm going to have my solenoid doing this. And I'll have a switch here and my battery. And then over here, there'll be a separate loop. So as I close the switch, we're going to see current flow this direction. Right? Which means in the solenoid itself, the way of trying to draw it, it comes out, in. So it comes out, in, out, in. If you want the dots and X's, here is the current. Everyone still with me?
Yeah.
All right. The magnetic field of the solenoid, does that field point to the left or to the right? Yeah, I'm not going to give this one to you guys. Someone needs to tell me. There we go. We say to the right. And I agree. Let's double check that. All right. So cross, I see current going inside. So I'm going to measure from the bottom. Current is going in at the bottom. I'm measuring the field inside the solenoid. So I'm measuring inside the solenoid. My magnetic field is going to the right. Same result if you do it from the top, right? So I'll do right hand from the top, right? Go from the top. Current is coming out towards you. I'm going to measure inside the solenoid. Magnetic field still to the right. So it's this game of rotating around in the solenoid, but always pointing to the right. So I'm going to say that's the solenoid, or what I'm going to call B external. That's the external one. All right. So let's focus on the loop's perspective. What did the loop see? Loop. All right. Did the magnetic flux go up or down? So I close the switch, magnetic field turns on, boom, starts going through the loop. So the loop went from seeing saw no V field, and we close the switch. So we say the flux increase, so the loop needs to induce a field going the other direction. It needs to induce a field that way. I was just to draw this dead on, so not 3D perspective, but just looking at it directly from the side. Right, there's the induced. All right, let's look at the bottom of the loop. Is the current going into the board or out of the board to create this magnetic field?
Is it out?
Let's try out. Let's try out. So if I go for out, right, so right, we said out of the board, that's a circle. So a circle, right? That's current coming towards you. I'm gonna measure inside the loop. Oop. Magnetic field to the left. Yep. And then up here correspondingly, current's going, let's see here, in, out, in response to this sudden increase in flux. All right. So now this is where I start to cry, because this is going to be one of my all-time favorite physics demonstrations, and I don't have the equipment with me because I am locked at home. So I found a backup video. We're gonna watch someone else do the demonstration for me, but still a good demonstration. Let's see if I can pull up the video for you guys. So we're gonna share. All right. So can everyone see the guy holding the copper tube?
Yes.
Yes.
All right.
Yes.
All right. So I'm gonna give a little bit of explanation just in case I haven't set up the audio to transmit correctly. So what he has here is a tube. You can just kind of see like a little slit open into it. When you see him drop the magnets, it'll become clearer what we're looking at. And all he's going to do is he's going to drop a non-magnet down this tube and then a magnet down the tube.
This lenses orchids. It demonstrates very nicely how magnets behave when they fall down metal tubes. We have a slug of metal here. Look at it.
So he's dropping a non-magnet first, and watch the speed at which it drops down the tube.
Drop it down the tube, and there's a nice window in the tube, so you can see all the way down. Oh, down she goes. Turn it down, go up, and still can go down at good speed. It's called gravity. Well, now, if we were to make a magic pass, drop it down again, something else might happen.
All right. So before I let this go on, he's playing with a copper tube. Does anyone know if copper is magnetic or not?
It's not.
Not magnetic. Our magnetic metals are iron, nickel, and cobalt. So, and that connection's unstable. So copper, not a magnet, but he's going to drop a magnet down the tube.
Extraordinarily slowly. The other way up. Oh my, magnetized, and this little buddy I showed at the beginning is not magnetized at all. The highly magnetized one is creating a little eddy current in the tube, which itself creates a little magnetic field that opposes the descending.
All right, so let's come back. Stop the share. Come on. All right, now we're back. So, what did we just witness? What did we see? We had ourselves a big hollow tube. We had a hollow tube, and he dropped a permanent magnet down that tube, right? He dropped the permanent magnet. And all of a sudden, the magnet was kind of floating down. It fell slowly. Its motion was damped, right? So what's happening, right? Looking at we'll look at sections, cross sections of the pipe, right? So we'll look at this section, and we'll consider this cross section. So, magnetic fields, they come out of the North Pole into the South. So as this magnet's falling, it's doing this. Gotta make these arrows a bit clearer. So it's coming out. And then on the other side, coming in, right? So as the magnet falls, this area, this is seeing increased flux as the magnet falls. So underneath the magnetic flux is going up and up and up. But above the magnet, this cross-section area, phi b, is decreasing. So I've got one part of the pipe that's getting more and more flux. The next part of the pipe is getting less and less flux. So I'll draw this picture again. Try to do this on the same. All right. So if the flux is increasing for this area, it needs to create a magnetic field in the opposite direction. So this guy says, fly back, create a field like this. Right. So flux is increasing, create a field to push it up, push the magnet back up. This one, the flux decreasing. So this guy's induced field points down. Make that legible. Induced. Right. So I'm going to redraw this from just a 2D perspective. Instead of looking down at 3D, I'm just going to look head on and see what it looks like. So side perspective, what do we see? All right, this guy. We see a current here. This current needs to make a magnetic field pointing up, right-hand rule. If I go current going that way, magnetic field inside the tube, magnetic field's pointing up. So there's the induced current there. For the top side, there's the current going the opposite direction. I say current, I need a magnetic field pointing down. Right. A equivalent way to think about the magnet as it falls, let's put the magnet back in. It goes north, south, north, south. What does this current loop look like? Remember, current loops look like magnets. They look like permanent magnets. So if I have a current going this direction, well, that looks like a north, south magnet. Whereas this one looks like a north. So as the magnet falls, underneath it, it's as if I am holding a bar magnet. North to north, they repel. So it's as if I'm holding a bar magnet trying to push the magnet up. On the other end, right, I see a north-south. They attract. They're trying to pull back together. So then it's as if I'm holding a magnet trying to stop the permanent magnet from falling. I'm trying to slow its motion down. I'm dampening the speed at which it falls. So, guys, I'm not gonna lie to you. This is one of the most important demonstrations of Lenz's law that we can talk about. Ever heard of electromagnets? Ever heard of your electric batteries, your cars move around? How many of you own one of those flashlights where you charge it by shaking it and you hear that thing going click, 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 up and down?
Yes.
That's what you're doing, right? There's a permanent magnet, and when you shake that flashlight, you're forcing that magnet to go up and down in a little tube. Well, by moving the magnet, you are converting your mechanical energy into electrical energy to power your flashlight. Right? Our whole technological world exploits properties like this over and over again. All right. Let's keep practicing this. All right. Let's do more of these. What's going on here? Oh, great. So my Wi-Fi seems to be cutting out. Thanks, that's not very helpful. Let's see here. We can hear but not see me. Let's try this. Close that down. All right, has this gotten any better?
A little bit, but it kind of goes in and out between being really crystal clear and then choppy.
Okay. All right. How do we want to handle this?
I mean, you're talking us through a lot of things.
Yeah. So, I'm gonna keep lecturing today. And what I'll do is I will post copies of my lecture notes, so you can at least go back, and I'll upload the video, though I suspect the video will have the same choppiness. All right. So we're gonna power through. We're gonna keep trying. I'll upload my notes, and we'll reassess Zoom lectures. All right. So let's keep going. All right. Let's try a practice problem. Let's say I have a loop of current. All right. All right. Here's my straight wire current. And I'm going to have a loop with some velocity. So I've got my loop, and it's flying towards the current wire. And the question is the direction of the induced current in loop. Basically, is it going to be clockwise or counterclockwise? So, way to figure this out, let's look at the current itself, just the current, and what magnetic field that current makes. So, right-hand rules, current's going up. If I measure to the left of the current, I see a magnetic field coming out of the board. So I see this. As a reminder, the wire is mu naught I over 2 pi r. All right, distance from the wire. So as I get closer and closer to the wire, the magnetic field strength goes up. So the way to represent that is the spacing between subsequent dots. Get closer and closer. So as I go that direction, the magnetic field is getting stronger and stronger. All right, so if my loop starts out here and goes that way, right. If my loop's going this way, then the magnetic flux is increasing again. So induced field will point, instead of out of the board, into board. I gotta get direction of current. Let's see here, in the board. We try. If I try current going this way, go in. Nope, got it wrong. So let's try. If I have current going down here, I get magnetic field going in. I induce. So that current is going clockwise. Induced current's going clockwise around. All right. More examples. Everyone okay for me to clean the board and go to the next example?
Key, wait a second.
All right, I'll wait. This is a great time for questions to go through the logic. I'll quickly run through it again while you think of your questions. So the setup was, I have a current, straight wire current going up, and I'm going to take a loop and just push the loop towards that current. Right? What we establish is the closer to a loop, the closer to the wire I get, the stronger the magnetic field. Magnetic field strength increases the closer I am to this wire. So, go back to loop. Loop sees little magnetic field, and a second later, as it gets closer, lots of magnetic field. So that's what I mean by flux has increased. It only had one dot, now it's got 3. So the flux increase, which means this guy wants to create a field opposing in the opposite direction. Right. All right, let's try one that's a bit trickier, right? So we're gonna keep, this is still more practice. Here's the setup. I'm gonna have a battery here, draw this correctly, and that's gonna go into a nice big loop of current. Switch. All right. So the setup is that I've got the switch. I can play when the switch is open or closed. And when I close it, I see current going around clockwise in this big part of the loop. And then I'll put a tinier loop inside. I'll put this guy in here. Right. A little bit. So what's the induced I in the inner loop? Let's induce current in the inner loop, and I'm going to do 3 cases, right? Close the switch, hold the switch, release the switch, right? So we're doing 3 cases. So A. Right after the switch is closed. Right after the switch is closed, what happens? We close the switch. We see a current going clockwise around. I'm just ignoring the switch to make life easy. Right. That's creating a magnetic field. Direction of current, inside the loop, boom, inside. So I see magnetic field created that way. And that's going through our little inner loop. So flux increase. The induced magnetic field points out. The induced current is going to be the opposite direction. It's going to be counterclockwise. Great. Ready for the next case?
Yes.
All right. So RB. I'm going to say, separate those. Long time. Long after the switch is closed. So looks pretty similar. Current still going the big loop. Current still going clockwise, which means magnetic field going this way. Right. So this is a critical analysis. I've held this switch closed for a long time, which means that the flux is constant now. The flux isn't changing. Right? If that flux is constant, there's no induced current. As long as I hold that switch forever and ever, doesn't matter that there is magnetic flux happening, right? Flux can be happening as much as we want, but because it's not changing, that's the key word, the change in flux. There's no change in flux, no currents being induced. Right. Final case, right? Which is right after the switch is opened. So what happens there? There was some magnetic flux, right? That's too sloppy. Try that again. We went from having some field present, final, so it went from some field to no field, which is to say that the magnetic flux decreased. We dropped the magnetic flux. Induced field. What's the words I use from Lenz's law? parallel to the external, which means that this guy is going to suddenly try and create a magnetic field that points in. Which correspondingly means a current that is clockwise.
Professor, use an X in both drawings.
Let's see here. Yeah, that's right. So on this one, all right, before, all right, so switch was closed, current's flowing in this guy. So a big loop, I see current going into the board. Then open the switch, kill that, no magnetic field from the big loop. Which means that the little loop went from having some flux, there were magnetic field lines going through it, and now the magnetic field lines are going away. So that induces, and this guy says, hey, try and replace what I just lost, because flux went down. So in that case, I want fields pointing into the board again. I want fields pointing in to replace what we lost.
Gotcha.
All right. So we're going to now naturally take the extension of this. There's this little game here of big loop, little loop, and each of them having currents through them. So, conceptual question, all right? When current flows in the small loop, when current flows in the small loops, it creates, if there's a current here, it's creating a magnetic field. It creates a B field. And look, there's a magnetic field going through here. There is a nice big loop. So that big loop sees magnetic flux from the smaller loop. So little loop creates its own magnetic field. That big field fluxes through big loop. So here's the question. Does the little loop induce currents on the big loop? Right. I'll draw this again. You got your big loop. Let's get that nice and centered. So if current goes through the little loop, that's creating a magnetic field. Boom. Well, that current's not constant, so this magnetic field from the little loop changes, which means that the flux of the big loop changes. Well, hold on. If the flux through the big loop change, that induces a current. So now current's induced in the big loop. And that big loop says, okay, try and create a current. And that changes with time, right? Well, the loop of the current of this guy's changing, which then induces a current back in the little one. And so there's this symbiotic relationship. One's inducing the other, and then back and forth. So the answer to this question is absolutely. That's absolutely important, right? As I take current through one, inducing the other, that one's going to induce back on the predecessor and back and forth. Right? This concept is what we're going to call mutual inductance. One induces on the other induces back. They're mutually inductors. So, like that. Catch all under this term, and we're just going to say inductance, the inductance. Here's the schematic way to think of this. Here's one loop, and I'll shift the other one. I'll put the other one over here. So I'll call this 1, coil 2. Coil 1's going to have some current. I'll label the lowercase I. It'll have some current going through it, which means it creates a magnetic field that does this. All right, so if I increase the current through this wire, if I increase I, does the magnetic flux go up or down? Yep, gotta go up. So, conclusion, the magnetic flux, the flux through coil 2 must be proportional to the current through this guy. I increase the current, change the flux. Decrease, decrease the flux. They are directly related to each other. There's some proportionality, right? Recall Faraday's law, right? Faraday's law says the EMF is delta phi B delta T. Well, if flux is proportional to the current, then I can just say that the EMF is proportional. Instead of the change in flux, it's the change in current. All right, so definition. We're going to define that proportionality. This proportionality here, that's going to be what we define as the inductance. Right? And so we'll write that as E equals L delta I delta T. All I've done is recast Faraday's law in terms of this L quantity. All right. So, great example of this. Go back to that solenoid. One of our favorite tools as physicists. Right. Let's say current starts to flow over here. There's a minute time gap before current flows here, before it starts to flow here. So there's current in this one, not there, which means that this loop will start to induce on this guy, right? Current in the left ring induces on the right, and vice versa. So a solenoid can be labeled as solenoids are also known as inductors. They are an inductor. They can induce on themselves. Right. With this equation that applies again, E is L delta I delta T. All right. So, comments. Inductors are analogs. Remember how we said capacitors, electric fields, right? Inductors are the magnetic analog Think of it this way. For an inductor, the voltage is equal to constant change in current, change in time. Recall for a capacitor, the voltage across a capacitor is the charge per capacitance. Right. Voltage equals quantity constant. Inductor. Voltage equals quantity constant. So that's what I mean by analogs, right? We'll be able to build new circuit components with our inductors. We'll be able to use them to construct new circuits. All right, we have this new L quantity. So what's its units? L is measured in henries. That's an H, right? So 1 Henry, voltage, henries, current, time. 1 Henry is equal to 1 volt seconds per amp. A volt second ampere is our units for inductors. All right. So, quick comment on this. Go to, say, like Wikipedia, look up the units of a Henry, and you will see literally an entire string of different equivalent ways to write this unit. There are so many different ways to define a Henry, and they're all equivalent. You just toy with, do I express this as joules or coulombs or whatever. So for our purposes, I'll stick with this one as much as possible. A Henry is a volt second ampere. All right. So I'll say this is a good breaking point. My next example will take about 10 minutes, and there's only about 5 minutes left in class. So I'm going to end the lecture here and wrap up this material on Tuesday of next week. So, sorry about the technical glitches, guys. We will try and find a way to resolve that.